I'm Weidi. In this talk, I'm going to present Seastar, Vertex-centric programming for graph neural network. Graph neural networks, or GNNs, are designed to extract rich information from graph data, such as social networks, knowledge graphs, and more. In the figure below, the performance of GNN models are marked with red boxes. As can be seen, GNNs achieve better performance than traditional methods in many graph tasks, such as node classification and link prediction. The computation pattern of GNN can be characterized as Seastar, and we illustrate with the left figure. The pattern of GNN layer is like star from the view of a single vertex. GNN datasets usually contain the graph structure and the initial feature of vertices and edges. In the source stage, features of source vertices are first transformed using neural network operations such as linear layer. In the edge stage, the feature of source, destination, and other edges interact with each other. The aggregation stage aggregates the transformed feature to the center node. Finally, the aggregated feature may go through more neural network operations before they are fed into next layer. We show two examples of this Seastar pattern on the right. On the top is graph convolutional neural networks, or GCN. GCN simply aggregates neighbors' features by summing them up. Below is the graph attention neural network, or GAT. It additionally computes an attention score on each edge, which indicates the importance of different neighbors. Existing GN frameworks provide various programming abstractions to help users to program GN models easily. DGL provides the graph abstraction. Feature vectors are grouped into tensor, then stored in the graph. Graph provides methods for conducting computation. For example, the update all executes two functions for the whole graph, one message function and one reduce function. In the shown example, the copy U function creates a message tensor M by copying feature from vertex tensor X. The sum operator then reduces the message tensor M according to the destination and names the output H. PyTorch geometric PYD and the new graph require users to organize GNN computation into stages of tensor-wise operations. Specifically, PYD provides message and update abstraction, while new graph has the SAGA pattern. GraphLearn and Euler focus more on sampling-based training. GraphLearn provides a Gremlin-like API to express the sampling operation. They rely on the tensor operations of deep learning backend, such as gather and segment sum in TensorFlow. For the execution, tensor materialization is the most commonly adopted approach. Users construct input as tensors, and within each stage of the Seastar pattern, tensor operators of backend deep learning systems are carried out one by one. Across stages, scatter and gather operations are inserted by the users or by the framework. DGL proposes the general-purpose sparse matrix multiplication, or GSPMM optimization, which implements specialized kernels when using built-in message function and reduce functions. We identify the limitations of existing GNN systems as follows. Though their programming abstractions are expressive enough, users need to cast the vertex-centric pattern into a whole graph and coarse-grained tensor program, which may be non-trivial, especially for complex models such as multi-head graph attention neural networks. Besides, users need to learn a set of low-level tensor operations or a set of domain-specific APIs. For execution, tensor materialization causes high memory consumption and bad data locality due to frequent data movement. GSPMM optimization only covers a limited set of operator combinations and still delivers unsatisfying performance due to the kernel design, as we will compare in our experiments. To address the limitations, Seastar provides a more intuitive Vertex-centric programming model. Users can program GN models with native Python constructs, such as list comprehension and reduction. Seastar then dynamically compiles the user-defined model into fast and efficient kernels. We show GACN and GAT's implementation using Vertex-centric programming model. For the GCN model, user writes a simple Python function with center vertex v as argument. Within the function, users can access the neighbor list with v.inNeighbors. For each neighbor node u, we can access each feature vector by using the dot operator. Then we use list comprehension to construct a list of neighbors feature. Finally, we sum the list and return the output. Similarly, for the GAT model, we first compute feature list E by sum center vertex V's feature and its neighbors. Then we perform leaky ReLU and exponential function on the result. The alpha is the attention score, which is computed by normalizing each element in E by their summation. Finally, we multiply the feature of neighbor vertex U with the attention score alpha and return their average. It's clear from the figure that the benefit of vertex-centric programming is bidirectional. Users can implement a GN model easily, and users can learn the GN models by checking its implementation directly. Next, we describe the code generation process of Seastar. The tracer takes the vertex-centric program and records each operator in the forward computational graph with operator overloading. It also verifies the correctness of the user's program. We embed an auto-differentiation module to derive the backward computational graph from the forward computational graph. Both graphs then go through a series of optimizations, such as operator fusion, dead code elimination, constant folding, and etc. Seastar then generates and compiles CUDA kernels for the optimized computational graph. The generated kernel is then integrated into PyTorch or other deep learning backend. We use GAT to illustrate. The computational graph of GAT is shown in the figure, where rectangles are input data and circles are the operators. The tracer additionally annotates each operator to denote where the operator is executed. For example, the add operator takes input from source and destination vertex. Therefore, it should be executed on edges. We denote its graph type as E. Leaky ReLU only takes input from the add operation. Therefore, its graph type is also E. We denote the sum operator's graph type as A, which stands for aggregation. Then the operator fusion optimization fuses the computational graph into two operators marked in gray region. Please refer to our paper for details of the fusion algorithm. This is the optimized backward graph of GAT. The whole computational graph can be fused into a single kernel. Next, we describe how Seastar executes the fused kernel. We first explored the feature-wise parallelism by using FAT. Now, FAT is a group of consecutive threads. FAT's size is determined by the feature vector size of vertices, and is said to be a power of 2. For the first few layers of GNN, the feature vector size is usually large, so the size of feature group is also large. In the figure, we show a case where feature size is 16, and we set FAT group size to be 16 too. Each FAT group is assigned a single destination vertex. The FAT visits the source edges one by one and carries out the computation and aggregation sequentially. This strategy avoids the aggregation conflict at the destination and improves the data locality of destination's feature, since it only is to be loaded once by a single FAT group. However, FATs may end up with skewed load, especially for power law graphs, in which some vertices have much higher degree than others. We also propose dynamic block scheduling. Specifically, we launch as many thread blocks as needed, so that the number of FATs is no less than the number of vertices. This approach alleviates the workload skew compared with static assignment. It also reduces the cost of atomic-based dynamic scheduling. To further reduce workload imbalance, we introduce vertex degree sorting. Our key observation is that in GNN training, graph structure is either fixed or is independent across mini batches. So we can sort the vertices in the background in their descending order of in degree. The benefits are twofold. First, we can further elevate the straggler problem by assigning early launched thread blocks to vertices in the front. In this case, computation of high-degree vertices can be overlapped with that of low-degree ones. Second, when feature size is small, a thread block can consist several FATs. By sorting, consecutive vertices will have similar degree. Therefore, FATs in the same block will have similar amount of workload. Intra-block load imbalance is therefore reduced. We compare the memory consumption and epoch time of Seastar with DGL and PYG using 3 models, GCN, GAT, and APPNP, on 9 datasets and 3 hardware platforms. Seastar uses less memory, especially for complex models trained on large graphs. For example, for training on Reddit dataset, PYG fails due to out-of-memory error for all 3 models. DGL only finished training of GCN, while Seastar is able to run all models. Seastar is consistently faster than other systems too. Seastar achieves up to 14 times speedup compared with DGL and 3 times compared with PYG. The better performance of Seastar is mainly due to operator fusion optimization and other kernel-level designs. We use a neighbor access benchmark to test the effectiveness of the kernel-level designs. The horizontal axis is the feature size of vertices. The vertical axis is the relative speedup compared with baseline. We use DGL's edge parallel strategy as baseline, and use Seastar's vertex parallel design as basic. We incrementally add FAT, sorting, and finally, we remove atomics. The result shows that Seastar is more than 900 times faster than baseline when the feature size is large. FAT and sorting can significantly improve the performance, especially when feature size is small. To summarize, Seastar provides a vertex-centric programming model to make it easier to write and learn GNN models. Seastar achieves better performance by applying optimizations such as operator fusion during compilation. This is at the end of presentation. Thanks.